took pictures.
We were car following.
That's okay. Cool. What other numbers did people come up with? What other numbers did you guys come up with? Any other numbers? I got 3,800, got 3,600, got 13,000. Ooh.
You got 13,000?
Oh, she got
So
13,000.
I had a standard deviation of like $7,000 though.
You had this big standard deviation. That's pretty big standard deviation. It's possible though. What else? What other numbers did you guys get? Any other good numbers? 63, 3,400, 6,300.
I got 8,800.
How big was your sample size?
30.
30. How big was the other sample sizes?
30.
Mine was 30.
30, 30,
like 46 or something like that.
46. How big was 15? What do you think the what do you think the shape of the distribution of car prices is? Skewed which way?
Right.
Right. Why is it skewed right? Why do you think it's skewed to the right?
College students can afford a Ferrari.
Yeah, most of the cars are probably going to be in the lower range, correct? Right? Probably under 15 grand, under 20 grand, most cars. Probably under 10 grand, really. Maybe 15. And then there's going to be a few that will be pretty pricey. So yeah, probably skewed, which would explain a high variability. It would also explain why your mean might be kind of big. What's up?
Is there like a way to calculate those Greek letters on this thing?
The Greek letters? Yes. There is, but I don't know it. On the 30?
Yeah.
On the TI-30, I don't know. There's a way to put data into it. Yeah.
I wanted to know.
Yeah.
Yeah, the answer is yes, there is. My answer is YouTube it.
Do you think the tutor center would know?
Oh, yeah, probably. I mean, I think if you just do mean, standard deviation, TI-30, whatever, and videos.
I'm assuming you will let us use stack crunch on our test.
No, what are those, the XS's? Yeah, there you go. Here's a good one right here. And it's 10 whole minutes long. Yikes, that is long. Let's skip to the good stuff. Yeah, there's a list editor. Yeah, there you go. It's right there. It's that button. Boom. Whatever that button is.
The data button?
Sure. Data, and then you put stuff in your list. Yeah. Yeah, so then you can input data, and then if you go into data, yeah. So go into data and go to list or go to edit or whatever, and then you can put data in. And then if you go back to your data menu again after you put stuff in your list, you can pick the list where all your data is stored and do like one variable stats. That one variable stats is really similar to summary statistics in StatCrunch. It'll calculate like your mean and standard deviation, all that good stuff. So yeah, it'll do it. But yeah, I would just YouTube it. It'll give you pretty specific instructions. Okay, so any questions before we get going? I'd like to take your activities sometime today. Yeah. Question?
I have a question on Empirical chapter 3.
Which question was it? So, is this the one? Heights of students?
Yeah, oh, but that, I think I figured that one out. Number 20, sorry.
Oh, not 19 or 27?
No, number 20.
Number
I
20.
said 19, but I figured it out and I forgot to delete it.
Oh, okay. A small internet business. He employs 9 people. Here's their salaries. Complete parts A through D. So it's gonna want A. What is it gonna mean and different values here. Mean, median, and mode. The quickest way to do this is gonna be to take that data and just pull it open in StatCrunch.
I tried to do a bar graph on StatCrunch and it was...
Well, let's see.
There's different parts to it though.
Yeah.
Oh, yeah, I know.
Okay. So first I'll go ahead and I'm gonna go ahead and get the stuff they want. They want the mean, median, mode. Oh, right, it's all here. So what is it, 50, 50, 50? There you go. 50. Check. Thanks. 50. Perfect. All right. The mode is 50. Cool. 3 down, 11 to go. The business is good. Benjamin has $25,000 to distribute to his employees. One option for distributing bonuses is to give each employee $2,500. Add the bonuses under this original plan to the salaries to create a new data set. So basically you have to do what? You have to add $2,500 to every salary? Is that true?
Is it times 9 or? That's employees.
The salaries earned by the employee are given him these are thousands of dollars. Okay? So I think this would be, they're in thousands, so this is like $2,500 that you're adding, right?
Yeah, so you added to,
So you would add that to all this data that you already have. Well, where do I think? Oh, it scrolls back. Oh, I hate that. You would add 2.5, right? So it would be 27.5, right? 37.5, 42.5. You could formulize this. There's a way to do a calculator on here, but I'm just going to do it this way. So 57.5 and 67.5, 77.5. Is that 2.5 more than everything? I think so. And it wants you to recalculate mean, median, and mode. And I think it's going to be, it's just going to raise the, well, anyways, we'll do it. It should just raise everything, right? Mean, median, and mode. Boom. 52.5, 52.5. Just took everything up 52.5. Ah. Okay. I'm guessing I haven't gotten to your question yet, huh? That's how it goes. Cool. Okie dokes. How do the mean, median, and mode compare to the originals? Hey, they all increased by $2,500. Boom. Perfect. Second option, he can give every employee a 5% bonus. Add the bonuses under the second plan of the original salaries, create a new data set. So this is where things are going to be annoying. So I'm going to give everybody, I'm going to do it in a calculator. So I think you can do, what's the one I want? Data, compute, and expression. What I want to do, I'm going to take everybody, so I'm going to take all of the original salaries, and I'll multiply them by, what do you give them, a 5% raise? Is that what it said?
Yeah.
So if you multiply them all by 1.05, that would give you the new salaries. And so I'll just call it 5% raise. Is that true? 5%. Okay. I think so. So let's go back to the stat crunch. Now we'll just do the same thing. So summary stats, columns. Have I gotten to your question yet? Whoa! That's not what I wanted. I only want the mean, the median, and the mode. Did I do the?
yeah, I think that was right.
What? Is that possible?
That's why.
Okay. That seems like it shouldn't work, but I'll take it. 52.5 for all of them? Why'd they all stay the same? All three, the mean, all three of them increased by 5%.
What are the odds of that?
Have I got to your question yet?
I guess.
Have I still got your question?
Probably put, why did you put 1.5?
1.05? Right, so if you get a raise, so if you have your salary, right? So your salary plus a 5% raise, right? So the 5% raise is 5% of your salary. Yeah. of your salary, and then here's your salary, right?
Yeah.
But if you factor out your salary here, that's just. So anytime you're trying to calculate a percent increase, you can just take your salary or whatever the price is times 1 point the raise. So you can do this. You can do this for like tax. Like if you're trying to calculate the price of an item after tax, you multiply it by 1.086 in the case of our counties, because our tax rate is 8.6%. So that's how you calculate a percent increase. That's why I did that. It was a 5%. Yeah? Okay. Did that answer your question?
Yeah.
Okay, yeah. You could do it like one column at a time and like calculate 5% and add it, calculate 5% and add it, but it's faster to do it like that. Okay?
On StatCrunch, is there a way to calculate like the frequency distribution, like all the ones, all the twos, all the?
Yes, I think so.
Because I kept trying.
I think so. Is it not a frequency table? So table's frequency for say var1. There you go. So what, a 25 pops up once, a 35 pops up once, a 40 once, 50 3 times. Yeah. Mm-hmm. Good question. Any other questions?
Yeah, how did you do that one more time?
Magic. It was in stat tables frequency.
Okay.
Yeah.
I had to redo one problem like 5 times because I couldn't.
That's dedication. I would have taken the 99%. Probably wouldn't have actually. Okay. Any other questions?
I tried to do a bar for the activity,
Mhm.
like with the bar years and the
Uh-huh.
price, and it just kept doing weird stuff.
Now, were you doing were you trying to do a bar plot,
Yeah.
or were you trying to do a histogram?
No.
Okay, so there's the issue. So bar charts are only appropriate for categorical variables. So if you were talking about, say, model or type of car, like SUV versus truck versus vehicle.
I
But
was just doing the years and price.
so if you're doing prices, typically years and money we treat as, that would be quantitative, right? And so those would be good candidates for histograms. So if you want, you would want to put your data back in, and rather than try to force a bar plot, do a histogram, and it should look a lot nicer. Yeah, so try that. Okay, good question. So remember, qualitative or categorical is bar chart, but quantitative, like numerical values, those go to histograms. Yeah. Otherwise, yeah, it would look all sorts of goofy, right? Yeah, I could see that happening. Yeah, you probably just got like a bunch of tiny bars.
Yeah.
Yeah, that's what we
Yeah.
in the Excel. 'Cause we
Yeah.
tried to fill it
You got like 40 different bars. Yeah, yeah. Because what it's doing is it's giving a bar to every single price.
Exactly.
You know. Okay. Any other questions about StatCrunch? Homework? Everything is grand? Yes, Bobby. What's up?
Just about the activity, did
Okay.
you do it? Did you find that average?
No, I haven't done it yet. I'm gonna do it. I haven't done it yet though. But I didn't get it. What was that?
So when you're late, do we get an extra credit point every day you're late?
Every day I'm late. You want an extra credit point?
Well, maybe.
Sure. What?
She said sure.
Okay, never mind.
Sure. Why not?
Okay, I have a question I found.
Okay.
Number 29.
Um.
It's part C though. I can give you the answers today.
Number 29.
Yeah.
Part C. Well, we could have different problems. Is the only issue. Oh, look at that. That's fun. Determine the sample standard deviation. This looks like a great job for StatCrunch. Because
It's the same one that I have.
is it the same exact data set? Okay, so you already got it.
Yeah.
Well, I'm already here, so I'm just gonna do it. But I believe you. Standard deviation. Compute. Boom. 0.0706. Blah 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 blah. Round to 3 decimal places. 0.071. Is that what you got?
But I don't. Oh, yeah.
Yeah, the numbers may be a little off. On the basis of the histogram to the right, comment on the appropriateness of using the empirical rule. does this look like the empirical rule seems relatively appropriate? What has to be true for the empirical rule to apply? What's that? Yeah, normal, right? So the key is we're looking for normality or like approximately bell-shaped. Does this look approximately bell-shaped?
Yeah.
Yes.
So one thing you're going to have to start becoming satisfied with in statistics is imperfection. This is about as normal as data is going to get. Okay? That's probably why I became a statistician, right? Because I'm not good enough for mathematicians. Close enough is good enough for me. Okay? This is about as good as normal is going to be. If you look at any data set in real life, it doesn't get much more normal than that. Yeah, it's a little bit higher here, but it's also not a huge data set. So I'd say, yeah, to me it looks pretty good. I would say it is approximately bell-shaped. So let's use it. Okay? And determine the percentage of candies with weights between 0.696 and 0.98 grams. Hint, use the sample mean, which they tell us is 0.838. So using this standard deviation, it looks like this would be, would this be 1 above and 1 below? Standard deviation? Is that true? So 0.838 minus 0.071, that would get you down to, no, that wouldn't be. That would be 2 standard deviations below. So this value right here is 2 standard deviations below the mean. And then this value right here, is it also 2 above, or is it only 1 above? It's 2 above. So these two values are 2 below and 2 above. So the rule says 68, 95, 99.7. So 68, this would be 95%. So the way I know it's 2 below, right, is you take this sample mean and subtract off a standard deviation once. That's not low enough. Subtract off the standard deviation again. That gets you down to the lower bound. Add it once, not big enough. Add it again. I think it is big enough. So I think it's 2. Okay? Was that your question on that part? Yeah. Now, to determine the actual percent, you would have to actually figure out how many are in that range and then divide it by 50. So you would just go through and say, oh, yep, 1, 2, 3, 4, blah, 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 blah. You know.
Between the 69 and 98 point.
Yeah, so you go in here. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You count them up, all the ones that are in that range. And then you would divide by however, well, there's 50 observations there. Yeah. And so you say, you know, oh, there was 47 out of 50. You divide it, and you get a certain percent in between. Okay? I don't actually know what the answer is, but it'll be somewhere around that. There shouldn't be many outside that range. Like I see 99 here. That's too big. But, okay? Yeah.
On the test, like, is it going to have any like tables where we need to find like the standard deviation?
Oh, nothing like that. No.
Nothing that big, but I mean,
I think if you look at the practice test, you'll get an idea, but I think there's like one on there that has maybe 5 or 7 observations.
do we have to show our work?
You don't have to. Yeah. If you get it wrong and you don't show your work, though, I'll just assume you guessed. If you get it wrong and you show your work, usually I can track down your mistake, so I can give you some partial credit for it. If that makes sense. So, yeah. The more work you show, the more likely you are to get points. Unless you get it right, and then I just assume you didn't cheat. Right. So, cool. Any other questions? Yes.
So you have a practice test on, is it on?
Yes. It is on my math lab. Go to course documents and go to practice exams. Boom. There it is. So you can grab it there. By the way, in case you didn't notice my new directions, I'm still kind of trying to figure out how the best way to take all these activities, because now I just got like a crap ton of Word documents, and I am almost done grading them, I promise. But so now I'm thinking maybe I'll just have you drop them all into folders rather than email them to me. So drop it. I labeled this folder Activity 2 Submissions. So drop them in that folder. I know some people have already dropped them in other random places, so I'll clean them up as I go. I mean, I'm collecting them from multiple sources, but that would be that's where I'd like you to get them eventually.
So I accidentally uploaded 3 individual, like I uploaded my graph, I uploaded my
Okay.
Excel,
I'll figure it out. Yeah.
Can you use that for the test?
No. You cannot. Sorry. Otherwise, we'd all have to have computers, and yeah, I don't have the capability unless we rented out a room or something. Plus, you can calculate the standard deviation of 7 numbers by hand. It's not that bad. I have faith in all of you. Okay, any other questions before we get going? Hey, we're only halfway through our class. Whatever. Okay, it's all good. Questions are good. If you had the question, probably somebody else did anyway. So, all right. So I'm moving on. We're almost done with chapter 3. We're gonna finish it today. Last time we talked, we were looking at other sort of measures of standing. So we came up with the quartiles, right? So the quartiles are where we split our data into fourths, right? Our lowest fourth, the next fourth, the next fourth, and the highest fourth. We mark off Q1 and Q3. Those are our first and third quartiles. The second quartile already had a name. It's the median. And we had an example of how to calculate it. Then I showed you the interquartile range. And one way we used the interquartile range was to test for outliers, and that's where we stopped. So we did an example. We calculated the IQR, got a lower and upper bound, sort of like fences or whatever. I don't know what your book calls them. I think they call them fences. And from there, we saw that, hey, this right here looks pretty unusual. That could definitely be an outlier when you look at the data set as a whole. All right? So the other way that we use the quartiles is in constructing the 5-number summary. So the 5-number summary, that's just your minimum, your Q1, your median, your Q3, and your max. Those 5 numbers together make the 5-number summary of a data set. And ultimately, we're going to use them to make a graph. All right. So, like for the data set we just had, we already calculated like all this stuff. The min and the max are the easiest ones to get, right? So for the 5-number summary, you would have your min, Q1. What was Q1 for this data set? If you look back in your notes. It was what? 735 for Q1. Was that right? Yep. And then what was the Q3? Like 4668?
Yeah.
And what was the median? We had to average 2 numbers, didn't we?
Yeah, the 1657 and the 1950.
Yeah, what'd that average come out to be? Something 5, I can't remember. 1805 was our average. Okay, and then once you have those, I mean, those are easy, or those are the hardest ones. The min's just the small one, and the max is 21,147, right? So you pretty much, we already had the 5-number summary. Now we just got to tack on the smallest and biggest value. All right, which is really cool and all. It's not that interesting. So the way we normally use these 5-number summaries is we create box plots. Okay. So for a box plots can be vertical or horizontal. They have what you do is you draw a box between Q1 and Q3. Wherever your median falls, you draw a line. Then from there, you would take, a whisk. Sometimes they call them whisker, like box and whisker plot. You take a whisker out to your max, and maybe a whisker down to your min. Okay. And if your data set has outliers, though, what they'll do is, where do I want to put this? Oh man, I did not plan this very well. I'll just show it down here. So, like in the example we just had, so you can create box plots 2 ways. Typically, you can either create them with showing the outliers or showing no outliers. And so if you had an outlier, for example, like in the data set we just had, then you would still draw your box plot, Q1, your median, Q3. But you would rather than going out to your max, if you had an outlier, you would star your outlier, and then here this would just be like the largest value that's not an outlier. So you only take your whiskers out to the next largest value, and then you just star your top value. So you show it on the plot, but then you also are indicating that it's an outlier. Yeah? That makes sense. So if your data set has outliers, you do it. If it didn't, then you wouldn't. Okay. Between the regular one and here? Well, basically it's like, okay, so you draw your box plot. I'll just show you. Let's do an example. Okay? You'll figure it out from the example. So we just did this one, right? So we have our data set, and our values range from, say, what did it go? 180 all the way up to 20,000. So we could say maybe here's $10,000, and then maybe this is $20,000. So this would be $0, you know, whatever. Not very well split. Okay, so what would that be? This would be 5,000. This would be 15,000. Okay. And if you go back to our summary that we had, right, what was our 5-number summary? So our min is 180. Our Q1 was 735. Our median was 1805.
Yeah.
Our Q3, 4668. And our max was 21,147. Now, if we weren't going to do anything with outliers, the way we would draw this thing is we'd say, okay, I need a box from Q1 to Q3. So Q1 is 735. That's way down here, right? Because this is like 1,000 right here. So 735 is way down there. So I need a box that goes from 735 up to 4668, which is right about here. Right, so here's 735, 4668. So that's my box. My median was at 1805, so that's way down here. Right? And then you'd have to draw your whisker down to 180 and all the way out here to 21,147. Whoa. Okay. Not very straight, but you get the idea. That's actually a really terrible line. Pretty embarrassed by that, but.
Wouldn't it be better to use the outlier on that one?
Well, let's see. So, what about. That looks really terrible. Can't handle that. Sorry. I'll probably make it worse. Is that better?
Not really.
The answer is supposed to be yes. Well, it's just got to, anyways, it doesn't matter. It's a little better. So what does it look like the distribution is? What do you notice about the distribution of the data? Super skewed, right? The first 75% of the data is all piled up down here, and then the top claims are all spread out. Yeah, so this is definitely a skewed distribution, and that's what box plots help us see, is they help us look for skewedness versus symmetry. But, of course, this right here we had flagged as an outlier, right? So if you wanted to show that this was an outlier in your data set, then you would actually you wouldn't do it that way. You would take your whisker wouldn't be nearly that long. You would just star out there and say, hey, there's this data point out here that's an outlier. The rest of my data just goes out to there. So you see that this distribution is actually still skewed even with the outlier, right? So it looks like the claims are still skewed, even if you just toss that out.
If you had more than one outlier, would you put it at each one, or
Mhm.
would you put it on the
Yeah, you'd have multiple stars. Yeah.
Why did your whisker stop there?
Oh, because this was my next biggest observation. Should have labeled it. Yeah, good question. That was at 10,034. Right? Make sense? So a box between Q1 and Q3, mark the median. Take your whiskers out to the min and max. Unless one of the min and the maxes happens to be outliers, then star them and bring your whisker back to the next nearest data point. Yeah.
So you would start 10, 0 through 4.
We wouldn't star this one because see that wasn't flagged as an outlier. So the only one I would star is this one out here. That doesn't really look like a star, does it? But that's what it was supposed to be.
Well, yeah, it's supposed to be a straight line too.
So critical today. I can handle it. All right, yeah. What else? Yeah. All right. I think that's it. So you can do these in StatCrunch. If you open up a data set, and I think I'll just pull one from maybe your homework real quick, because I think down at the end there are some that do. Let's see, it's got to be down here somewhere. This question's about box plots. Here you go. So here's a bunch of data. I'm going to open it in StatCrunch. It's just in the graphs menu like everything else was. So you go to if you go to graphs, just go to box plot. Now the question it'll want to know. So you should tell it where your data is, just like everywhere else. And the question is, do you want to have if you want to use fences to identify outliers or not? So if I don't do that, it's just going to give me a traditional box plot like that. If I do that, hopefully this data set had outliers to make an example. Damn, it didn't. Hold on, let me add a bad value. Let's say there was a value of like 6.5, an outlier. Blah, 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 blah. No outliers. Boom, right? Super skewed. Edit. Let's use fences to identify outliers. Boom, there you go. So it did. Yeah? Okay. Cool. Pretty easy. Not too bad? All right. So you'll have some chance to answer some questions about that on your homework. All right. Any questions before we move on? No? Then I'm moving on. We are going to chapter 4. We're just going to keep on trucking. Got it. Chapter 4 is not huge, though, so don't panic. All right. All right. Chapter 4. What we want to talk about now is our goal in chapter 4 is we want to talk about how we compare two different variables to each other. Okay. So a scatter plot, for example, right? A scatter plot is where you have, a variable 1, a variable 2. Your data is basically like ordered pairs. Right? So like for a single person, you observe two things about them. So maybe you observe their age and you observe the years of experience they have and you observe their salary or something, right? And for each person, you have two numbers. They're the years they've been working and how much money they earn or something. And you go and you plot those points, okay? And, they may or may not make some pattern. But that's how we're gonna create our scatter plots. Okay. What we're looking for is to see if there's maybe some way that the two variables are related to each other. Does one going up cause the other to go up, or vice versa? Does going down cause the other to go down? Okay. So that's going to be our goal here in chapter 4. We want to look at how two variables interact with each other. Okay. So we probably all made scatter plots or at least plotted points on an XY axis. So So here's an example of a data set that might be interested in comparing two different variables. So here's a bunch of cars, domestic vehicles, and it measured the weight of the car, and then it measured the average fuel economy of the car, right? So for each particular car, you have the weight, fuel economy, and just looking at the table, what do you suppose might be the relationship between these two variables?
Heavier the weight, the higher the MPG.
The heavier the weight, the
Lower the MPG.
yeah. So the heavier your car gets, you might expect the fuel economy to go down, right? Makes a lot of sense, probably. So let's see. So you could take this data, and we could make a scatter plot. So I'm just going to I got a little table up here, because sometimes every once in a while I get smarter, and I don't have to flip back and forth between things. So you can put either one. So the weight, I'm going to put the weight down here, and I'm going to put the miles per gallon right here. A lot of times what we think of as this variable on the x, what we think of as the x-axis, a lot of times we think of this as sort of what we'll call a predictor variable or explanatory variable. And up here, this is what we might call the response. The response variable, right? Because we think of, when you're thinking about the cars, right, it wouldn't make sense. It's not like you can reverse engineer the car and say, this car we made a car that was this many miles per gallon, and it caused the car to be this weight. I mean, you can kind of reason it that way. We more would think about, hey, we made a car that weighs this much, and it's caused the car to have this kind of fuel economy, right? So we'll plot this. So what does our range go? Our weights go anywhere from, what, a little under 3,000 up to 4,700. Does that look about right? So we'll say maybe this is 3,000, and what do we say? 4,700, so maybe 32, 36, 38, 4,000, 42, 46, 48. I'll go 5,000. That would cover all our bases for weight. And then for the miles per gallon, what does it range from? Anywhere down to 17 up to 26. So we'll just start maybe at 15, 20, 25, something that'll get us the general range. So you're just going to start plotting your cars. So car 1, it weighed 4,700 pounds, and it got 17 miles per gallon. Boom, right? The next car weighed 4,000 pounds-ish. It got 18 miles per gallon. The next car, 3,000, a little over 3,000 pounds. It got 22 miles per gallon. And these are just approximate, by the way. They're not perfect, obviously. 3,500 got what? About 19 miles per gallon. I don't know if you guys can actually see that data from where you're at. 4,000 pound car got about 19 miles per gallon. Another under 4,000 pound car got 19 miles per gallon. A 3,200 pound car got about 24 miles per gallon. A just under 3,000 pound car got 26 miles per gallon. A 3,500 pound car here got 19 miles per gallon. So it was about here. Another one right around there. And then a 3,800 pound car got, 18 miles per gallon? So around there. All right. So this is what our data looks like. And if you look at that data, what do you notice about that? A lot of cars get 19 miles per gallon. It's true. Could be the mode.
The lighter the cars, the better MPG it gets.
Mm-hmm. And what do you even notice about the pattern between the increase and the decrease? It almost looks like it follows what? What kind of? A what? Slope, skew. I don't know if it'd be a bell curve. Well, a bell curve really only applies when we're looking at one variable. We're looking at two variables here, so the pattern's definitely going down, right? You can almost imagine like it's kind of this nice sort of general sort of pattern. Yeah. Okay. Yeah, it almost has this was almost like a linear pattern. All right. And that's actually what we're interested in this chapter. That's what we're looking for. Okay. See if the data has some sort of linear relationship to each other. In this case, I would argue it looks like it probably does, right? At least pretty linear. It's not perfect, right? Okay. So what we're talking about here is we're talking about different forms of linear correlation. So this is what we're going to be hoping to get towards. We want to look to see if variables have some type of linear correlation. And linear correlation can be both positive or negative. Okay. So like if you have, a data set, a scatter plot, and your data looks something like this, right? This would be what we would call positive correlation. And it is linear, right? You can see that it sort of follows a linear pattern. Again, remember, you're never going to get data to behave perfectly, right? There's no way that every car produced is going to follow this perfect line where its weight tells you exactly what miles per gallon it's going to give. There's always going to be some variation in your data. So that'd be positive correlation, meaning as one thing goes up, the other thing goes up. Of course, along with that, we also have variables that can have a negative correlation. Okay. So what do you think, what are some examples of things that might have a positive correlation? Right? So we saw one.
Age and height, maybe? Like, the older you get, the taller you get?
To a point. Yeah. Do you think it'd be linear?
No, I think old people get shorter.
Old people get shorter. It's true, actually. So the one thing, there are, so these are the ones we're going to be concerned with. There is nonlinear correlation, right? So you can have, data that does this, right? Nonlinear. You could have data that does kind of this, right? This is nonlinear, right? And actually, probably, if you look at the heights of people over time, what would it probably actually look like? Which graph would it probably look like? Well, it can't come down too far because it's not like we shrink back to 0 inches by the time we die, right? So, yeah, some weird sorry, I'm thinking of Benjamin Button right now, so got some weird. Except for you still grow and then you go back to. Anyways, all right. It'd probably be like I think it would look like one of these. Which one? Yeah, it's gonna look like this, right? Because you have a maximum height eventually, and you reach it, and then you just kind of level off. So that's probably what it looks something like that. So probably not. So it probably wouldn't be linear because you grow really fast from baby to whatever 14 or something, and then your growth kind of slows down, or 16 or whatever. What else? What else do you think might have a linear trend in a positive direction? Like as one goes up, the others goes up.
The more you eat, the more weight you gain.
So it could be maybe. I don't know. Could be.
Say you eat a crap load of food and I don't gain no weight.
Okay.
I'm just letting
Good.
everybody know.
There you go. So maybe I don't know. Let's think of something we can be more sure about.
What about years and car prices?
So would that be the older it is? Are you saying the model year? Are you saying the model year, or are you saying how old is the car?
No, I just mean as time goes by, car prices go up.
Oh, so you're actually talking about inflation.
Yeah.
Do you think is inflation linear?
No.
I'm gonna go with no.
It keeps going up.
It does. I think inflation is actually exponential. Because if inflation is a percent increase, but the thing is that the percent increase is on the price of the percent increase, so it's kind of like compound interest, right? So we might have 2% interest this year, and then the price of something that costs $1 goes up to $1.02. But then when next year when you have 2% inflation, it's 2% on $1.02. So it goes up more than 2 cents, right? And it just keeps compounding. So, but I like your idea with car prices and years, right? I think you're right. It does a linear trend. I was thinking about the age of the car over here maybe, but you could think about it as model year. So I was thinking of the age of a car and its price. Disregarding maybe like the day after you drive it off the lot and now you no longer have a brand new car because it depreciates pretty fast. But after that first year, cars tend to depreciate pretty linearly for at least 10 years. They tend to go down in pretty linear fashion. Obviously, there's a bottom line because, eventually your car kind of levels off at $1,000 or something. But yeah, go ahead.
What about like temperature outside of ice cream sales or something like that? Would that be?
Yeah, so if you look at things like if you look at the average temperature and maybe popsicle sales, that's true.
How about the more money you have, the happier you are?
Yeah, to a point, maybe linear. To a point, they say there's a point where more money doesn't make you happier. That's what studies have shown. Yeah. Studies have shown that up to a certain level of earning, the money does bring you happiness, but after that point, the increased earnings don't actually increase your happiness. And
Those studies were done by poor people.
the finding is it happens on the individual level right around $75,000 a year. And beyond $75,000 a year, they find that increases in price don't significantly increase people's happiness beyond that point.
That's it.
Well, yeah, I don't know.
But who knows? Depends on a lot of factors. Yeah.
Because I saw the popsicle one, it just reminded me that like the rate of ice cream sales goes up as the temperature rises because, and murders or something. Is it? Do you remember?
Yeah, that's actually true. That's something we're gonna get at because there's a difference between correlation and causation, which we'll talk about. But yeah, if you were to actually plot ice cream sales, of like the local ice cream truck, and then like the number of murders per state in that week or that month or whatever, yeah, there actually would be a nice positive association, and it would show that as ice cream sales go up, the number of murders go up. Yeah, and there's a lurking variable, and it's temperature and it's season, because murder rates go up in the summer because people are outside. There's more opportunities, I guess, to murder in the summer. Yeah.
Well, I was thinking about psychology, but I was thinking of another comparison between ice cream and drownings during the summertime.
Yeah, so that's another great example. So if you look at ice cream sales and the number of drownings, it would be a nice positive correlation, which of course means that if you eat more ice cream, you'll probably drown or something. I don't know. Does ice cream cause drownings? Probably not. Because you get cramps. Anyways, yes, okay. Hold that thought. We're going to come back to that, okay? Yes, that is true. Correlation does not necessarily imply causation. That is absolutely true. There's actually there's a website where they look at like spurious correlations, where they talk about variables that are related to each other that really shouldn't be related to each other at all. Anyways, okay, so you can have positive correlation or negative correlation. And so the idea here is we want to get, plots are really cool to look at, but we also want to have some numerical value that helps us understand how strong a linear correlation is. So as statisticians, what we've come up with is this correlation coefficient, okay? And we use a lowercase r to denote the correlation coefficient. Now, if you look in the book, there's this really awful formula for calculating the correlation coefficient, like just really terrible. It's just, but I'm not going to make you actually calculate correlation coefficients by hand because I think that's cruel and unusual. But here's basically the idea. So if you had two variables that were perfectly linearly related, like they all fell on a perfect line, that would have a correlation coefficient of +1. If you had a correlation and all your values fell on a perfect negative line, okay, that would be a correlation coefficient of -1. And if you have a correlation coefficient of or if you have data that has absolutely no pattern to it, yeah, that would have a correlation coefficient of 0. Okay. Now the thing is, something to remember though, is that the correlation coefficient only measures linear correlation. Okay, so for example, you could have a plot that looked like this. Two variables like that. Are those two variables related to each other? Do they have a nice, relationship? They follow a nice pattern? Yeah, I mean, there's definitely a pattern. It looks like they almost follow a nice parabola, like a quadratic. But they're not. It's not linear at all. So this would actually have a correlation coefficient of 0. So, because it's nonlinear. Okay? So just be careful. It only measures that. So R can be, I'll just put some note here. So it measures linear correlation. It's always between -1 and 1. Okay? And if it's negative, then that means you have negative correlation. If it's positive, it means you have positive correlation. And the closer it is to 1, it means the closer your data is to a perfect linear relationship. That's the idea. Okay. We're actually pretty good at guessing correlation coefficients usually, just because we have pretty good recognition of visual patterns. So I linked to this little practice thing here, where you can actually, if you take that link, you can actually visit it and you can guess correlation coefficients, because that's probably what you all want to do today when you go home, is guessing correlation coefficients. So here's some plots. So thinking about the rules of correlation coefficients, would this one have to be negative or positive? Negative. What about this one? Negative. Negative. This one looks like it would be what? Slightly positive. So this one has to be which correlation coefficient? This one has to be the 0.4. So notice, it's not a super strong linear relationship, but you can still see it, right? With your eyes, you can kind of recognize that. What about here? Between these two, which one's stronger, do you think? You think this one might be stronger? The bottom. Which one's the strongest linear relationship? This one. So what correlation coefficient would it have to be? Yeah, it's got to be this one, right? Closest to 1. These ones between these two, if I have a sneaking suspicion this one is the stronger linear relationship. Only because there's less variability, and notice you have a couple out here and a couple out here that continue the trend. So I would probably go that way.
Is it when the dots are closer together, it's stronger, but when they're more scattered?
When they're closer to a line, yeah.
Okay.
The closer it is to linear. And I did pretty good that time. So here you can see again, right, the same idea. This one's slightly positive. This one's very strong negative. And then these two are negative. These ones are pretty close. Actually, I don't know how you would guess between the two, but maybe that. I got those wrong. I switched them, but they're pretty close. Okay? So we're going to do a little more with that and then actually talk about how you use that data to do predictions tomorrow.